Hello and welcome to the video on electrons in the atom. This will start our second unit in chemistry. Well, I guess it's a little bit into the middle of the second unit in chemistry, but it really gets into what is in the atom in terms of the electrons, how they work, and why they are important. Before we get there, I remembered that I had forgotten to talk a little bit more detail about what metals are and what nonmetals are. So I wanted to look at the physical properties of metals and nonmetals before we get into the details of their electrons, because a lot of these properties are actually due to the fact that they have electrons and how many of them they have and what their arrangement is. So if we look at metal first, metals have high electrical conductivity, whereas nonmetals are poor electrical conductors. And as you can probably guess already, most of these are going to be opposites of each other. Metals have high thermal conductivity, so not only are they good conductors of electricity, but they are also good conductors of heat, which you know if you've ever done any baking, of course, because your pans get really hot in the oven, whereas nonmetals are really good heat insulators. Which is why if you want your house to be warm in the wintertime, then you do not want to be in something that's metal, because they are really good conductors of the energy, of the heat that you want to keep inside. Whereas if you have a wooden house or a brick house, those are nonmetals and those are better at insulating it. Metals are typically gray or silver, and they have a luster. So in other words, it's sort of like being shiny. So they have a metallic gray or silver luster. Whereas nonmetals have no metallic luster at all. Metals are almost all solids at room temperature. And whereas nonmetals can be solids, liquids, or gases. Again, this is at room temperature. Metals are malleable, which means they can be hammered into sheets. Whereas nonmetals are brittle in the solid state. Metals are also ductile, which means that they can be drawn into wires. Nonmetals are non-ductile. So you can obviously make something that looks like a wire out of a nonmetal, but you have to have a larger piece and then just cut it smaller and smaller. Whereas with metals, you can make it molten, so you can make it hot, and then you can just pull it out into a long wire. Metals have high melting points, whereas nonmetals typically have lower melting points. And metals have higher densities than nonmetals. And when we are looking at the periodic table and we're looking at the atoms and where they sit on the periodic table, these physical properties of metals and nonmetals make sense, especially in terms of their densities and melting points and those things, because that's why they are placed where they are on the periodic table. So now let's go back and review for a minute the different models that we have for the models of the atom. And we had talked about this previously. So we have the Thomson model of the atom, which in the 19th century, he said the atom was a ball of positive charge containing a number of electrons. We then went to the Rutherford model in the early 20th century, when he said that most of the atom's mass is concentrated into a small positively charged region called the nucleus in the center, and the electrons were all over the place. Then we came to Bohr's model, which he said, no, I'm not quite sure that really works. I think the electrons travel in definitive orbits. And then we have come to the quantum mechanical model, where we say that there is a neutron, so that's agreed upon, but in the quantum mechanical model, the electronic structure is more about a probability and where you're more likely to find something than where it actually is. So if we think about this, all of these models have to take into account the fact that you have positively charged particles in the nucleus, along with neutrally charged particles in the nucleus, and then you have negatively charged particles around the outside. And so when we're looking at this, the question is, why aren't these negatively charged particles on the outside, the electrons, attracted enough to the protons for the atoms to just collapse? And what is it about them that makes them continue to stay farther away from each other? So one of the things that I want to focus on here is that Bohr said that the electrons are in concentric circular paths or orbits, sort of like the planets around the sun. And he said that the reason the electrons don't fall into the nucleus is because the electrons are in a particular path of fixed energy. So we're going to talk about Bohr on this side over here. So he said that there are energy levels, meaning that there are particular places outside the nucleus where electrons are most likely to be moving. Sort of like if you are thinking about a staircase. Okay, if you're going up or down a staircase, then the electrons are found on each stair, not hovering in between the stairs. So we have energy levels of an electron which require electrons, that's my abbreviation for electrons, E negative S. So this requires electrons to change energies to move. And this means move closer to or farther away from the nucleus. So when Bohr was thinking of this, he wasn't really thinking of it in terms of steps. He was thinking it more in terms of a ladder. And so he said that if you think about a ladder and the rungs of a ladder here, that the lowest rung of the ladder is the lowest energy. And I'm just going to use a capital E for energy. You can go up the ladder one rung by one rung, just like an electron can jump from one energy level to another energy level. Just like we can't put our foot here halfway between the steps, the electrons can't be there either. So if there's an electron sitting here, it can jump up a level, or if you give it lots of energy, it could potentially jump up 2 levels, but it can't go part way. And then that would also mean then that you can jump down levels as well, 1 or 2, if you lose energy. So when this was thought about and people were trying to figure out, well, how much energy is this going to require, they came up with the idea of a quantum of energy. So let's look at how this is slightly different. Rather than looking at it as a ladder, like we did on the last page, let's go back to my original thought of it being a staircase, as we see here. And in this idea, when we're talking about the quantum mechanical model of the atom, we're not quite there yet, but we're getting there. But at this point, what we have is a quantum of energy. A quantum of energy is the amount of energy required for an electron to move from one energy level to the next higher energy level. So again, the amount of energy required for an electron to move from one energy level to the next higher. And these energies of electrons, therefore, are said to be quantized. What that means is that there is an abrupt jump from one energy to the next. It's not a slow build-up. It is, we don't have enough energy, yep, we've got enough energy, and we are going to jump. Now, if you'll notice here, the energy levels of these stairs are not even like they were in the ladder. There's a different amount of energy required to go from the nucleus to the first level, and from the first to the second, than there is, say, from the third to the fourth. or from the 4th to the 5th. So the spacings here are not even. They have more energy required to make this jump than to make this jump here. So when you get up to the higher energy levels, once an electron, let's say an electron started here on the first energy level, and it got enough energy to jump up to the second, and then it got enough energy to jump to the third, it doesn't need nearly as much energy added to get to the 4th or to the 5th. So as you get farther and farther away from the nucleus, it gets easier and easier for the electron to move, which means it's easier and easier for the electron to escape the atom. Now, in 1926, Erwin Schrödinger decided that these atomic models were good, but you needed a little bit something else, dealing especially with this idea of quantized energy. And he came up with the quantum mechanical model, because basically what he's saying is that there is no definitive path for the electron to take around the nucleus. Instead, there's a really good probability of where you will find it. So all of this led to the quantum model, which again says no definitive path for the electrons, just a probable position. Now, Schrödinger and his quantum mechanics and the quantum mechanical model really are quite complicated. So most of the time we're not going to be talking about this particular model because it's not as easy to understand. But basically what it does for the electron is, because it's just a probable position, it changes the idea from there being particular energy levels to being an electron cloud. And the electron cloud is technically what we understand now to be happening. The cloud is denser, where the probability of finding the electron is higher, and it is less dense, where the probability of finding the electron is lower. So, okay, if that's all well and good, we now have the idea that this model of having steps or the ladder isn't quite right. We really should be talking about a cloud, but the whole idea of there being energy levels and what that means is still super important. And so that's what we're going to talk about next, is the whole idea of atomic orbitals. There's a lot of information on this page, a lot of pretty pictures. But let's take a look first at the chart in the upper right. So basically what the quantum mechanical model says is that every energy level of electrons is designated a principal quantum number. Basically they're given a number, all right? And it's over here on the left-hand side, it's the principal energy level. We give the number n, or we give the level a number equivalent to n. So n is 1, 2, 3, 4, etc. We also then say within each principal energy level, electrons can occupy energy sublevels. Similar to people in a theater, when they sit in a theater, their seats are arranged by section, which would be the principal energy levels, and they occupy particular rows within those sections, which are the energy sublevels. So again, if you go to the theater, the section you're in is the principal energy level, which would be your n value, and your row would be your energy sublevel, which would be numbers 1, 2, 3, 4, etc. So now, if we look at the table below, we look at the number of energy sublevels, and we notice that it's the same as the principal quantum number. So, for example, if you have a 5th principal energy level, if I were to add a n equals 5 over here, then there would be 5 sublevels. The sublevels we talk about as being orbitals. What kind of orbitals do the electrons have within each of their sublevels? So the electrons, remember, are not fixed to a circular path. They have regions where they're likely to be found. And so these regions can't really be called orbitals. In the quantum mechanical model, these regions are called atomic orbitals, even though they're not actual orbits. The letters denote the atomic orbitals. The s orbitals are spherical, and that's what I'm showing over here in yellow. That is what an s orbital looks like. So the electrons in the s orbital are somewhere in a sphere. Beyond that, the p orbitals are dumbbell-shaped, and you'll notice that the p orbitals can be in the x, the y, or the z direction. So if we put all of these orbitals together, the P, X, Y, and Z, you can end up with an atom that looks like this, or the electrons anyways, that look like this, where you have the 1s shell in the center, and then you have all of these different blue spots where the electrons could be in the P shape. Now, the probability of finding an electron elsewhere other than these colored regions is slim to none. If we continue on with these, as you notice in the chart, it goes S's, then P's are added, then D's are added, and then F's are added. So if we continue with these pictures, we start with a spherical, then we go to like a dumbbell shaped, then we go to another shape that's, I don't know what you want to say, they're sort of dumbbell shaped, but there are 4 of them instead. And so then the d orbitals can look like any of these. Now notice that this last one is a little bit weird. We're not going to worry about why it looks like this. Just wanted to show this to you. And then from the d orbitals, we can go to the f orbitals here in red. And again, the places that electrons can be when they are in the f orbital is very bizarrely shaped. So when we put this all together, it ends up to be a cloud of electrons that we are looking at. So you don't have to memorize these pictures. I just thought they were really cool to give you an idea of what each individual section of the cloud looks like. So if we summarize the principal energy levels, sublevels, orbitals, and electrons in here, there is a mathematical relationship between your principal energy level, the number of orbitals that are there, and the number of electrons. And this is super important. What this information's telling, you must know. So if we are in the closest orbital to the nucleus, so this one here is closest to the nucleus. So it's the smallest. We call it energy level 1. It has n squared number of orbitals, so 1 squared is 1. That orbital is called the 1s because it's in shell 1 and it's only the first kind of orbital. How many electrons it can hold follows the rule of 2n squared. So in the first orbital, n being 1, you can have 1 times 1 squared, or 2 electrons. If you go larger in terms of how many levels you have of electrons, you will notice that you rapidly increase the number of electrons that you have. In the second orbital, you have both s and p shells, and you can have a total of 8 electrons. In the third orbital, there are 3 subshells, s, p, and d, and you can have a total of 18 electrons. In the fourth orbital, you have 4 shells, S, P, D, and F, for a total of 32 electrons. So basically what this is saying is that there's a mathematical mathematical model of explaining and figuring out how many electrons are going to be where. To make this simple in terms of clarifying it in your head, if we make this be the nucleus in the center here with neutrons and protons, and again, I'm just simplifying this out. This first shell is going to be the first energy level, n equals 1. You can hold 2 electrons. The second shell, energy level 2, can hold 8 electrons. The third shell can hold 18 electrons. Okay? And you can continue to do it like this. Notice that I drew the electrons together in pairs. We're going to talk about why I did that in class tomorrow. So at this point in time, I would like you to answer one question that I have posted along with this video in the description on Blackboard. And again, that question is to explain how the quantum mechanical model of the atom describes the electron structure of the atom. Do your best to answer that in a paragraph form, submit it to Blackboard, and we will continue this discussion tomorrow in class, and I can answer any of your questions then. Bye for now.